Hello everyone, this is part 1 video on past year NEET questions from the chapter thermal properties of matter in physics. We'll start with a question that has come in the year 2019. A copper rod of length 88 centimeter and aluminum rod, unknown length. So aluminum rod length is not given. Have their difference in length independent of temperature. Means what? Say for example, initially let us say the length of the aluminum rod is what? L. So this is the length of the aluminum rod. Okay. Now what is happening is, irrespective of the temperature, the length is remaining, the difference in length. They have their difference in length independent of temperature. Means if you consider temperature change of delta T, then the copper length will be what? Length of copper at any different temperature will be what? Original length of copper, which is 88 centimeter into 1 plus alpha copper into delta T. So the linear expansion formula. Now the length of aluminum after that temperature change will be equal to what? L into same 1 plus alpha aluminum into delta T. So they are saying the difference in length means what? The modulus, we can say modulus of aluminum and copper, the difference is basically what? Independent of temperature. Okay, so which means what? Look at this, we'll subtract. So look at the difference will be what? This is L plus L into alpha aluminum into delta T minus, we have to subtract this, right? This is what? 88 plus 88 alpha copper delta T. Okay, so this is what? Minus 88 alpha copper delta T. So here if you look at it, right, there is this term L minus 88 that is anyway independent of temperature. Other term is what? L into alpha aluminum minus 88 into alpha copper. This entire thing is multiplied by delta T. If the difference in length is independent of temperature, means what? This particular term should become 0. Then only the difference in length will be what? Independent of temperature, isn't it? Means what? That L, which is the original length of the aluminum, into alpha for the aluminum should be equal to what? 88, which is the original length of the copper, into the alpha for the copper. So what do we have? The final relation is what? If this condition has to be satisfied, right, what is the final relation? Length of aluminum L into alpha aluminum, what is it? 2.2 into 10 power minus 5. Units are anyway same for both the alpha, that is why we are not keeping the units, is equal to what? 88 into alpha copper. What is alpha copper? 1.7 into 10 power minus 5. 10 power minus 5 is cancelled. So L will be equal to what? 88 divided by the 2.2 will go to the other side. Divide by 2.8. 2.2 into 1.7. So we can see here 2.2 ones and 2.2 40s. So this is like what? 40 into 1.7, that is 68. Unit is going to be centimeter, because the length of the copper is what? In centimeters, right? So length of aluminum also will be centimeter. So what is the answer for this question? It is option A. So what are we doing? The difference in length, right, is independent of temperature. So that is the basic principle. And here we are using the thermal expansion concept. What is it? For any rod, final length is equal to what? Initial length into 1 plus alpha delta T, thermal expansion formula. So here it is a rod, so we are using what? Linear expansion. Next we have a question. This is like a question where we'll use both the Wien's law as well as the Stephen's law. This question has come in the year 2018. The power radiated by a black body is P, and it radiates maximum energy at a wavelength lambda naught. Okay, so that is the initial situation. If the temperature of the black body is now changed, means we are changing the situation, temperature we are changing, so that it radiates maximum energy at a wavelength 3 by 4 lambda naught. The power radiated in the second case is what? N times of P. It is not N subscript P, it is what? N times of P. So original power radiation is what? P. Now it is what? N times of P. They are asking what is the value of this N. So look at it. So we have two cases. Case 1. Let us say the temperature of the black body is T naught on the Kelvin scale. Here what is the radiation power coming? P. And what is the wavelength with maximum intensity, that is lambda naught. Second case, the power is becoming NP and the maximum radiation, the maximum energy radiation is what? 3 by 4 lambda naught. So here we need to find what is the temperature. So you'll use what? Wien's displacement law. So what is it? For a black body which is giving out radiation, the lambda corresponding to the maximum intensity emitted, and temperature will be related as what? That lambda m into T is equal to what? Constant. The Wien's constant, but here no, we don't require this constant value. Okay, so initially what is it? Lambda naught into T naught is equal to what? Finally what is the corresponding maximum intensity wavelength? 3 by 4 lambda naught into T dash. So what we'll have? Lambda naught is cancelled, so 4 by 3 T naught, that is our T dash. So the new temperature of the black body is what? It is 4 by 3 times original temperature. Now why are we looking for the temperature of the black body in the second case? Because when we want to relate the radiation power, right? Radiation power is related to what? The absolute temperature from the Stephen's law. So initial power they are saying is what? P. Initial radiation power is what? P. So here the surface area and the other things are constant. So what is it that we'll have? The power, initial power is proportional to what? T naught power 4. Second case, the power is what? N times P, right? That is proportional to what? The temperature T dash is what? 4 by 3 T naught, right? Power 4. So if you divide both of them, means what you will get? Np by P is equal to what? 4 by 3 T naught power 4 divided by T naught power 4. Tp is cancelled. Here also T naught power 4 is cancelled. So 4 power 4 by 3 power 4. What is 4 power 4 means? 256. 3 power 4 means 81. So N value is equal to what? That is on the left hand side, right? What is it? 256 by 81. That's it. So here what did we do? By using the Wien's displacement law, we are able to relate the second case temperature to first case temperature. They didn't even give us what is the initial temperature. So we assume it is some T naught. So we are able to get second case temperature is what? 4 by 3 times T naught. And Stephen's law or Stevens-Boltzmann's law, what is it? The radiation power is directly proportional to what? Fourth power of absolute temperature of the body. So from there we are able to get what is the N value. This is an important question. It's based on what we call as the equivalent thermal conductivity. So in fact we'll see one more question which is in the similar model, but let's understand what is the concept. See, in normal current electricity, right? So we have the resistors like in parallel or resistors in series arrangement. In that case what we will say, the combination of resistances can be replaced by one single resistance. We call it as what? Equivalent resistance. This is what? Series. Same amount of current will go through them. This is what? Parallel. Parallel means the resistances will have the same potential difference between them. This is something that we learn in the 10th standard also. Anyway, we'll see it in 12th as well in current electricity chapter. Okay. But if you have a series means the equivalent resistance is what? R1 plus R2. Parallel means the relation is what? 1 by R equivalent is equal to what? 1 by R1 plus 1 by R2. So this is what we have in the context of the current electricity. Now if you have any resistor, right, which is maintained at a potential difference delta V and resistance is R, what is the electric current through that resistance? potential difference by R. Similar to this, if you look at a conducting slab, okay, so for a conducting slab, the heat is driven because of the temperature difference. So in case of the electric current, the driving force is what? Potential difference. In case of heat current, what is the driving force? Temperature difference. So we have the conduction rate of heat transfer to conduction. What is it? Ka by L into delta T. We can rearrange and write. Check it how we can write it. We can write it as delta T by L by Ka. This is similar to what you see in the normal current formula. Voltage by resistance, right? So this particular term, this L by Ka, is also called as thermal resistance. So the heat current means what? The amount of heat flowing per given time. Heat current will be equal to what? Temperature difference by thermal resistance. So now when you have the slabs also can be connected. They can also be connected in series or parallel. When the slabs are connected in series or parallel, right, we will get what is the equivalent thermal resistance by using similar principle, like the way we use in electric current, right? Series means what? R equivalent is equal to R1 plus R2. Parallel means what? 1 by R equivalent is equal to 1 by R1 plus 1 by R, like that. Okay. So whenever we have a question on equivalent thermal conductivity or thermal conductivity of the composite slab, like that, so we have to use this series and parallel arrangement, like the way we discussed in the case of current electricity. So let us take a look at it now. So here what is it? We have two slabs. This is slab 1, slab 2. We see the heat is flowing parallel in both of them. This is what parallel. Series means what? One slab will be like this, other slab will be like this. So whatever the heat coming through slab 1 will have to go through slab 2. So series resistors means what? Whatever the current coming through the resistance 1 will have to go through the current in the resistance 2 also, correct? So here what is the arrangement that is given to us? It is the parallel arrangement. Okay, so we have two slabs. We need to find what is the thermal conductivity of the composite slab. So let us see how do we approach this question. So here the two rods A and B, they are made up of different materials welded together as shown in the figure. So this is what? This side is temperature T1, this side is temperature T2. So heat is going to flow like this. As we said, what is it? This is like the parallel arrangement. Their thermal conductivities are K1 and K2. The thermal conductivity of the composite rod. So here you see from the geometry, right? Both these rods are having the same length. What is it given as? D. Each of the rod is having same length, that is what? D. And cross section area, you look at it, it's identical. Means if rod A, cross section area is A, rod B also is what? Same value. Now for the first rod, what is the thermal resistance? It's like our R1. R1 is what? Length, which is D, divided by thermal conductivity K1 into A. For the second, length is D divided by thermal conductivity is K2 into, both of them have the same area of cross section. Now if you replace both of them by a single slab, what is the length of the slab? D. But what about the area of cross section? It is like what? A plus A, 2A. Thermal conductivity, we call it as K equivalent. So R equivalent will be what? Length of this particular equivalent slab is D divided by K equivalent into area is what? 2A. Now in case of parallel, what is the formula? 1 by R1 plus 1 by R2 is equal to 1 by R equivalent. That is the formula, right? So 1 by R1 means what? Reverse. 1 by R1 means what? K1 A by D plus 1 by R2 means what? K2 A by D. This is equal to what? 1 by R equivalent means 2 times. So I'll write it at the top. So since we got these expressions, so let us just remove some part here. No, we just remove this and then we'll write it at the top. Okay, so look at it. What is going to be the relation? 1 by R1 plus 1 by R2. Already we have the values. 1 by R1 is what? K1 A by D. 1 by R2 means what? K2 A by D. This is equal to what? 1 by R equivalent, reciprocal of this, which means what? K equivalent into 2A divided by D. So we'll see both sides denominator D is cancelled. K1 plus K2 into A is equal to what? 2 times K equivalent into A. A is also cancelled. We look well. K equivalent means 2 will come this side. What is it? K1 plus K2 by 2 is equal to what? K equivalent. Now don't think that this is like a standard formula we can remember. It is going to change from geometrical arrangement to geometrical arrangement. But what will remain same is the principle. Parallel means what? In terms of thermal resistances. Thermal resistance means what? Length of that slab or rod divided by thermal conductivity into area of cross section. That is the thermal resistance formula. Just like the way we have in current electricity, series means what? R equivalent is equal to R1 plus R2 like that. Parallel means what? 1 by R equivalent is equal to 1 by R1 plus 1 by R2 and so on. So same principles we'll use here also. In fact, we'll see that the next question that we'll discuss in another video, we'll have the series combination. So here we have the parallel combination. In that case, we'll see it will be series combination. Okay. We'll go to the next question. This is based on the Stephen's law. A spherical black body with radius 12 centimeter radiates 450 watt at 500 Kelvin. If the radius were halved and the temperature is doubled, the power radiated will be something. So means what? We have two cases. Initial case and the final case. Initially, what is it? The radius is 12 centimeter. Finally, what they are doing? Radius is half, means R dash is equal to what? 6 centimeter. Initially, what is the temperature? T is what? 500 Kelvin. T dash is what? The temperature is doubled, means 2 times of 500, which is what? 1000 Kelvin. Initial power is what? 450 watt. They are asking what is the final power. That's it. So Stephen's law says what? Radiation power is equal to what? Sigma A T power 4. Sigma is the Stephen's constant for a black body. A is the surface area. T is the temperature on the absolute scale or Kelvin scale. So here we can see that sigma A will be what? Spherical, right? So spherical body means what? What is the surface area? It will be what? 4 pi into R square. So 4 pi R square into T power 4. That is the initial. Final P dash is equal to what? Sigma 4 pi R dash square into T dash power 4. That's it, right? So we'll just take a ratio of them. What is it? P dash by P is equal to what? So 4 pi sigma, everything is cancelled. What we'll have? R dash square T dash power 4 by R square T power 4. That is the ratio. Okay. Now we'll just have to substitute the values and we can get the answer. That's it. So what is it? R dash is 6 and R is 12, right? T dash is what? 1000. So look at it. P dash by P is what? 450 watt is equal to what? It's like, R dash by R the square. R dash is what? 6. R is what? 12. 6 by 12 means 1 by 2 square. T dash by T power 4. T dash is what? 1000. T is what? 500. 1000 by 500 means 2. What is it? 1 by 2 square, 2 power 4 means net we'll have 2 square. What is it? 4. So it means P dash is equal to what? 4 into 450 watt. That is nothing but 1800 watt. So it's a case scenario question. Like first scenario, second scenario based on the Stephen's law. So we'll see that a lot of questions we got in the previous years based on the Stephen's law and then Wien's displacement law. Next we have a question that has come in the NEET paper 2 of 2016. This is based on the idea of calorimetry, but it's a little bit of a theoretical question. Two identical bodies are made up of material for which the heat capacity increases with temperature. Means both these identical bodies, right? They are made up of the same material. Means let's say we have a body 1 and body 2. They are made up of the same material and identical. Means geometrically they will be what? Identical. So not bother too much about the drawing here. The understanding is what? They both are identical. Since they are made up of same material means what? They will have the same mass. One of these is at 100 degrees Celsius, other is at 0. Means, let us say this is at 0, this is at 100. If the two bodies are brought into contact, assuming no heat loss, the final temperature will be how much? Now generally, right, so imagine when we talk about the heat capacity. So what is the heat capacity? It's nothing but the heat that is absorbed or released divided by the temperature change. So this will assume to be independent of temperature. Generally we assume this to be independent of temperature. Identical bodies means same, made up of same material. If the heat capacity is independent of temperature, right, means if you bring them to contact, what normally would happen? Both of them will come to 50 degrees Celsius. Like, when you want to increase the temperature of this body from 0 to 50 means here heat has to be absorbed. For how much temperature change? 50 degrees. Whatever the heat that is absorbed, same heat will be released when this object is decreasing the temperature from 100 to 50. Okay, so here what is the heat released? Heat released is equal to what? Just looking at the relation, it is what? Heat capacity into the temperature change. So here heat absorbed will be what? Heat capacity into the temperature change. Okay, so if the heat capacity is not changing with respect to temperature, what we will expect? Here the 50 degrees rise and here 50 degrees decrease, so that both of them will come to the final common temperature of 50 degrees Celsius. That is what is normally expected. But here what is happening? The heat capacity is increasing with temperature. Means what? At high temperature range the heat capacity will be more. So high temperature range means what? When we look at the object 2, its temperature is changing from 100 onwards. This is the high temperature. So here the heat capacity will be more. So really if we try to bring both of them to 50 degrees Celsius, right, then this will be requiring some amount of heat. This will release some amount of heat. But since here the heat capacity is higher, means what? When we bring both of them to 50, here we will have some more energy that is being released than what is required. So this side there is an energy requirement, this side there is energy release. Since the heat capacity here is higher, which will have what? The energy released from this side will be more than what is the energy required on the other side. Which means if you really bring them both of them to the 50 degrees Celsius, we will still have some surplus amount of heat. So which means what? The hot body will not really come down to 50. Maybe it will come down to some, 55. We will not know what is the exact value, or a 60. When it comes down from 100 to 55 or 100 to 60, that heat itself is sufficient to bring the cold body also to that particular temperature, because in the low temperature range the heat capacity is what? Less. So what we will see is that the overall temperature will be what? The final temperature or equilibrium temperature, whatever we call it, will be more than 50 degrees Celsius. If the heat capacity is independent of temperature means exactly we will hit 50. In high temperature range, heat capacity is increasing with temperature means what? We will have the equilibrium temperature more than 50. What if it is the reverse? If the heat capacity is decreasing with temperature, then what we would be having? We will have final temperature less than 50. But here the question is what? The heat capacity is increasing with temperature, so the final equilibrium temperature will be what? It will be more than 50. Okay. Next we have another question, NEET paper 2 of 2016. This is a straight question based on the Newton's law of cooling. A body is cooling from a temperature 3T to 2T in 10 minutes. Okay, means here the rate of cooling is what? Temperature drop is a T, time taken is what? 10 minutes. So this is the rate of cooling. Okay, The room temperature is capital T. So here what is the room temperature? It is taken as what? Capital T. Now look at it. As per the Newton's law of cooling, the average rate of cooling is equal to what? A constant C into the average temperature of the body minus temperature of surroundings. Average temperature of the body means what? It is coming from 3T to 2T, means it will be 2.5T. 3T plus 2T divided by 2. So which is what? C into 2.5T minus T. That is what? C into 1.5T. That is the relation. Okay. So from here we can cancel the T also, and we will get the what is the C value. So here what is the C value going to come? C will be equal to what? The 1.5 also will come to the left side denominator. So what we will have? C will be equal to 1 by 15 minute. So this is what is the C value. Assume that the Newton's law of cooling is applicable. Okay. The temperature of the body at the end of next 10 minutes will be, means we have to find what will be the temperature of the body at the end of the next 10 minutes. So here look at it. So at the end of the next 10 minutes, let us say the temperature is becoming what? T dash. Then decrease in temperature is what? 2T minus T dash divided by time is what? 10 minutes is equal to C into average temperature of the body, means what? It is coming from 2T to T dash. At average temperature means what? 2T plus T dash by 2. This is the average temperature. Okay. Minus temperature surrounding is what? Same, right? It is not changing. So look at it. What is it? 2 is cancelled. So it is T dash by 2. That is what we'll have inside the bracket. The temperature difference, average temperature value minus the temperature of surroundings. So when you subtract temperature of surrounding, what do we have? The T will get cancelled. We'll just have what? T dash by 2. Now here this T dash is what we are asked to find. So look at it. The C value we'll take it as what? 1 by 15 minute, right? Means what? 2T minus T dash by 10 minute is equal to 1 by 15 minute into T dash by 2. So 15 2s are what? 30. 10 1s, 10 3s. Cross multiply. We'll have what? 60 minus 3T dash is equal to T dash. Means 60 is equal to what? 4T dash. Means 60 by 4. That is what? 3 by 2 into T. That is our T dash value. So what is the final temperature of the body at the end of the next 10 minutes? It will be what? 3 by 2 into T. Okay. So this is a straight question based on the Newton's law of cooling. So one scenario, we'll be able to get what is the value of that constant C in the Newton's law of cooling expression. We'll take the value and substitute in the second equation. So generally whenever we have the questions in Newton's law, right, we'll have these two scenarios, scenario 1, scenario 2, like that. Okay. We'll move on to the next question. This kind of question has come in multiple years. It has come in the NEET paper 1 of 2016 as well as the 1999. The coefficient of linear expansion of brass and steel, alpha 1, alpha 2. Length of the brass is what? L1 and steel is L2. If L2 minus L1 is maintained same at all temperatures, which one of the following relations will be holding good? See, if you, so initially what is the length of the brass? L1. What is the coefficient here? Alpha 1. What about the steel? It is length is L2 and coefficient is alpha 2. If you change the temperature by delta T, right, the final length of the one is basically here representing brass is equal to what? L1 into 1 plus alpha 1 delta T. So this is coming from the linear expansion formula. Similarly, the final length of the second, which is in this case the steel, will be equal to what? L2 into 1 plus alpha 2 into delta T. So the L2 minus L1 should remain same at all temperatures. Means what? This is the L2 at a different temperature. This is the L1 at different temperature. So look at this. L2 final minus L1 final is equal to what? We have to do this minus this, which is what? L2 plus L2 alpha 2 delta T minus L1 alpha 1 delta T. So in this, right, we will have L2 minus L1 plus L2 alpha 2 minus L1 alpha 1 into delta T. So this they are saying should always remain the same. Means what? This will be anyway constant term. L2 alpha 2 minus L1 alpha 1 into delta T. So as temperature is changing, right, this delta T will be changing, which means the overall difference, this is the difference in length, right? So we'll see the difference in length will depend upon the temperature. It should not. Means if it's not depend upon temperature, means what is the only possibility? The term that is multiplying delta T should be 0, right? So what is the term that is multiplying delta T here? It is L2 alpha 2 minus L1 alpha 1. This must be 0. Means what? L2 alpha 2 should be equal to L1 alpha 1. That's it. So if you have that relation between L1 alpha 1, L2 alpha 2, then what will happen? The difference in length will be what? Maintained same at all temperatures. It will not depend upon the temperature. So what is the correct answer for this? Option B. Alpha 1 L1 should be equal to what? Alpha 2 L2. Next we have a question which is like, mixing mechanics with the principle of calorimetry. Okay, so look at this. A piece of ice falls from a height h so that it melts completely. So how it is going to melt? Because when it is falling from a height, it will lose its potential energy, right? So that energy must be converted into heat. So we'll read through the question. Only 1/4 of the heat produced is absorbed by the ice, and all the energy of the ice gets converted into heat during its fall. Means when it is falling, right, say for example the mass of that ice is m, it is falling through a height h, then the energy released or lost will be equal to what? M into g into h. It is falling through a height h. Okay, that is the loss of the potential energy. All of this is converted into what they are saying, heat. So once it is falling onto the ground or something, all of this energy is converted into what? Heat. So this much amount of heat is being produced, but only 1/4 of the heat produced is absorbed by ice. Means heat absorbed by ice is what? Only 1/4 of this. So what is the amount of the heat absorbed? It will be 1/4 mgh. Okay, by using this absorbed heat, the ice will melt. See, for the melting of the ice, right, what is the latent heat? It is 3.4 into 10 power 5 joule per kg. The heat required for melting is what? M into L. M is the mass of the ice into latent heat. So both of them we should just equate it. So what we are going to get? M into L is equal to 1/4 mgh. Here mm is cancelled. We are looking for h, by the way. H is equal to what? 4 times L by G. That is our h value. So 4 times L is what? 3.4 into 10 power 5 divided by G is what? 10. Everything is in the SI system. So it will be what? 10 power 4. What is 4 into 3.4 means that is 13.6 into 10 power 4. Everything is in the SI system. So this is like what? 136 into 10 power 3 meter. That is what? 136 kilometer. So look at it. If the ice is really falling from that much amount of height, theoretically, right, then if even 1/4 of that energy released is converted in the form of heat and is absorbed by the ice, then ice will be able to simply melt. This is something that we will see not to a significant extent, but to some extent, like when we have these raindrops coming with small pieces of ice, right, when they fall onto the ground, it's a different thing that they will break down. But what is also going to happen is the heat released, right, will also be able to partially melt them. Okay, so for this question, what is the answer? It is 136 kilometers. Simply what are we doing? We are just taking whatever is the heat released and based on the condition that they are saying 1/4 of the heat is absorbed by that ice, we are equating it to whatever is the heat taken by the ice for the melting, which is mass of the ice into its latent heat. Next we have another theoretical question. This is based on the Wien's displacement law. This has come in the year 2016, paper 1. A black body is at a temperature 5760 Kelvin. This is the temperature of the black body. The energy of the radiation emitted by the body at wavelength 250 nanometer is U1. Wavelength 500 nanometer is what? U2. Wavelength 1000 nanometer is what? U3. Wien's constant is 2.88 into 10 power 6 nanometer into Kelvin. Which of the following is correct? So they're asking us the relation between the U1, U2 and U3. So look at it. No, so we have, when we look at the Wien's displacement law, what it actually talks about, when you look at the spectral intensity, spread of energy based on the wavelength, you will have a typical curve like this. So this particular lambda is what we call as lambda maximum, or the wavelength that will correspond to maximum intensity. So lambda m into T will be B. Lambda m into T will be equal to what? B. So for this body, right, for the black body, what is the temperature? 5760 Kelvin, right? Means what? Lambda m into temperature is 5760 Kelvin is equal to what? B is 2.88 into 10 power 6 nanometer Kelvin. So lambda m will be equal to what? 2.88 by 5760 into 10 power 6 nanometer Kelvin. So here what we will be able to see is that the denominator, right, we can write it as what? We can write it as 5.760 into 10 power 3. Okay, so what we will be having, the 10 power 3 and 10 power 6 means 1 10 power 3 is cancelled. So what do we have? This is like what? Lambda m is equal to 2.88 divided by 5.76 into 10 power 3 nanometer Kelvin. So this is what? 2.88 once, 2,000 by 2 means what? This is 500. Okay, so Kelvin is also cancelled, so we'll have just nanometer. So what is the wavelength where we'll have the maximum intensity? Is lambda m is what? It is nothing but 500 nanometer. And the other two wavelengths given, 250 and then 1000 nanometer, they will be, so 250 will be somewhere on this side, left side, 1000 will be on the right side. So what we see here is, since the lambda m is coming as, luckily here they have given the numbers in such a way that they will be able to perfectly cancel off. Okay, so when we see this graphical representation, right, what are we going to have? We'll have a representation like this, isn't it? So which means the 500 nanometer, right, that will correspond to what? The maximum energy intensity, which means, you know, U2 will be the one among all the possible wavelength, right? The spread of energy will be maximum where? In the case of the 500 nanometer, which means clearly U2 will be more than U1, U2 will be more than U3. This is what we can say. And while by graph wise we might be able to draw some conclusions between U3 and U1, that will be little bit not so appropriate. So the one that we can clearly say is what? U2 will be more than U1 as well as U2 will be more than U3. In fact, U2 will be more than the energy given by any other wavelength. That is why we call it as what? The wavelength which is giving us the maximum intensity, right? Which means what is it that we can clearly say from this data? U2 is more than U1. Okay, so in fact the given options, which of them is the appropriate one? U2 is more than U1. But what do we know? U2 will be not only more than U1, U2 will be also more than U3. But the comparison between U3 and U1, right, we will not be able to derive that quick conclusion, because it depends upon the general spread of the graph. But what we can clearly say is the peak value, right, will be more than the other two. Okay, so the correct answer for this is what? Option B. Next we have a question based on the thermal conductivity. This has come in the cancelled paper of 2015. Two ends of a metal rod are maintained at temperature 100 and 110. The rate of heat flow in the rod is found to be what? 4 joule per second. Means what? So two ends of the rod, we are maintaining at what temperature? This is at 100, this is at 110. So what is the rate of conduction, or rate of heat flow through conduction is what? 4 joule per second. If the ends are maintained at temperatures 200 and 210, means, you know, it is a different scenario. They are saying let us take it out and keep this between 200 and 210. Now what is the rate of heat flow? They are asking what is the rate of heat flow. See, remember, whenever we have conduction, right, the rate of heat flow through conduction. So what is the rate of heat flow through conduction? It's a straight formula, right? What is it? Ka by L into delta T. K is the thermal conductivity of that material of which the rod is made up of. A is the area of cross section. Is the area of cross section. In both the cases, A is same, by the way. L is the length. Same rod, right? In both the cases, that is also same. So if you see, delta T means what? Temperature difference between the ends. It has got nothing to do with what is the actual temperature. So in the first case, if you are to write the expression, right, this 4 joule per second is what? K. Of course, we don't know the value. Into A divided by L. Delta T is what? 10 degrees. Second case, we have to write the same expression, means what is it? Here also K. Area is not changing. Length is not changing. What is the temperature difference? Here also 10 degrees only. From 200 to 210 means what is the difference? 10. From 100 to 110 means difference is what? 10. So in this case also, what will be the expression? Ka by L into 10, right? So this is also nothing but what? 4 joule per second. So in this case also, the rate of heat flow will be what? Same, 4 joule per second. It is not going to change. Why? Because the rate of conduction will depend upon the property of the material K, thermal conductivity, geometrical properties, area and length, and then the temperature difference. It will not depend upon what is the actual temperature in both the ends. It only depends upon temperature difference between the both the ends. Okay. Since the temperature difference is same in both the cases, the rate of conduction or the rate of heat flow through that conduction also will be same in both the cases. Okay. So what is the correct answer for this? Option B is the right answer. So with this we completed the part 1 discussion, and we'll see in the second part video.